any tangent line to this curve, like this, tangent line here. So let's say we draw a tangent line here. That's the tangent line almost at 1, 1. And how about if we draw a tangent line here? Or if we draw a tangent line here, will any of these tangent lines pass through the point 1, 3? What do you think? If we draw any tangent line to the curve, y equals x squared, do you think this tangent line, any tangent line to this curve, do you think that would ever pass through point 1, 3? What do you think? How does it look like? No.
No.
It doesn't seem like any tangent line is going to pass 1, 3. And so in this case, if you look at the picture or the diagram or the graph, it kind of looks clear. It kind of looks trivial. But, again, you cannot prove anything by a diagram. Okay? All right? So you cannot prove anything by a diagram here. So now, on example 7, your job is to what? Prove or show that that there is no tangent line which will pass through the point 1, 3. So now, how many tangent lines are there? There's zillions of tangent lines. There's a tangent line at every x value. So there's zillions of tangent lines, and none of the tangent lines will pass through point 1, 3. That's what you have to show. Is that clear? So the question is, how do you do that? Now let's hold that example 7 for a moment. And now example 8 is now kind of related. Okay, so let's look at example 8. Example 8. Show that every tangent line to the curve y equals x squared lies below the curve y equals x squared. All of these examples, example 7 and x, are kind of related. So if you look at example 7, we have example 8 now. Example 8, it says here, show that every tangent line to the curve y equals x squared lies below the curve y equals x squared. So now, if you look at this diagram here, same diagram, I drew many tangent lines here. Now, when you look at all of these, if you look at all of these tangent lines here, do you see that the tangent line is always below the curve? Do you think that is the case for the curve y equals x squared? Of course, this is not generally true, but for the curve y equals x squared, it is true. So again, if you look at the curve y equals x squared, this curve right here, and draw a tangent line, this tangent line is always below the curve. It's always below that curve. So how are we going to show that? How are we going to show that? So do you think you have any ideas? So any ideas here? Now in both of these problems, example 7 and 8, the first step is this. When you look at this problem, we have y equals x squared, and they both talk about tangent lines, but they do not give us the tangent points, right? There's no tangent points. 1, 3 here, this is 1, 3, and that's not the tangent point. So let me just erase this part right here. Let me just erase this tangent line. How can I erase this tangent line? Let me see. There we go. So that point is 1, 3. So in both of these cases, example 7, example 8, again, both two questions are actually related. Okay, they're both examples are on about tangent lines to the curve y equals x squared. But in both cases, the tangent point is not given. So when the tangent point is not given, then what do? Then we have to make up, because we always need a tangent point. So in this case, both example 7 and 8, the starting point is actually the same. So both example 7 and 8. So let me write it down here. So first, find equation of tangent line at what? A comma f of A. Oh, by the way, by the way, never call this guy x. If you call this guy x, that will be a critical mistake. So find the tangent line to the equation at A comma f of A. Tangent line to the curve y equals x squared, that is, at A comma f of A. So this is the starting point. This is the first thing you have to do, whether you use example 7 or use example 8. The two questions are different, but the first part is the same. First, you have to get what? You have to get the equation. So now let's look at that. So now what? And this a comma f of a, that's a comma a squared. So let me write that down. That is equal to a comma and then a squared. That's a comma a squared. So that's what we have. And then now, what is this here? Now, y is equal to x squared, so what's y prime? Y prime, yeah, we know that. Y equals x squared, then y prime is 2x. So what is the y prime? What is the slope of the tangent line? Can you tell me the slope of the tangent line at that point? Slope of tangent? What is the slope of tangent line at a comma a comma a squared? A comma f of a. What is that? What is the slope of the tangent line at a comma f of a? That is the slope of the tangent line to the curve at a comma a. So let me just put a parenthesis here. Okay, a parenthesis. Slope of the tangent line to the curve at a comma f of a. What is that equal to? Somebody tell me the answer.
2a.
That's right, 2a. Now note that this is 2a, not 2x. If you call this guy 2x, that is now going to blow up the entire problem. It is very critical that you have 2a as the slope and not 2x. So let me say this here. This is what? Not. So this is what? This is not 2x or any other letter, not 2x. So the equation becomes like this, which we have seen this equation so many times now. This is now y minus a squared is equal to 2a times x minus a. And note that the slope is 2a, not 2x. The students make the mistakes sometimes, and so I need to put a square here. So that's that. And that's the equation. And then of course you can you can always get the equation. You can write this in the slope intercept form. So that will be 2ax. That will be 2ax. And then we have minus 2x squared, but then add a squared to both sides. Minus 2a squared and then plus a squared, that would be minus a squared. So the equation will actually be like this. And this, by the way, we can actually call this the what? Yeah, we can. Yeah, anyway, we get this. Okay, so that's the tangent line, and we can actually call this guy L of x. Now, for example 7, what do we do? We substitute the point 1, 3 in here, x and y. Now, you know what? There's a solution file there's a solution to, I have a file here right next to this guy, which is a solution to example 7. So I'm not going to finish here, okay? And I'll talk about that. And then now let's look at example 8. Example 8, now, this is the line y equals L of x. Now, how do you show that all of these tangent lines lie below the curve? How do you show that? What is it that we have to show? Note that this is not y equals f of x. This is our what? This is our f of x. That's our f of x. And now let's look at the tangent line. So tangent line, why don't we just pick one randomly? So let's say that we have a point now, a tangent line. Now this is example 8. Let's say we have a point right here, and we can call this guy A. Now, okay, like this. And then what? And then call this guy y equals L of x. Then what is it that we have to show? To show that this curve is, the tangent line is below the curve, what is it that we have to show? This tangent line actually depends on A. So I can actually call this guy, if you like, L sub A of x If every tangent line actually depends on A. Or just simply L of X is okay. In this case, what I'm saying is this point right here is A. So in this case, example A, what is that we have to show? So here, the hard part is the logic. The calculation is really simple. So when you look at these questions like example 7 or example 8, they are logically difficult questions. Once again, the calculation is super easy. There's almost nothing to calculate. Well, there is some. It's not like there's nothing to calculate. There is, but again, when it comes to the calculation part is really simple. And of course, you don't need a calculator, okay? So you have to, in these kind of problems, the question is a logical question. You need to understand the problem, and you have to formulate the problem. You have to formulate means you have to know what you need to do mathematically. Okay, so this is f of x, y equals fx, and y equals z of x. Now, to show that every tangent line lies below this curve, what is it that you have to show? You can tell me what you have to show? So we pick a line y equals lx here, y equals lx, that's the equation of the tangent line. If we were to show that this tangent line lies below this curve, y equals f of x, what is it that you have to show?
Is it b squared minus 4ac greater than equal to 0?
What? What is it again?
B squared minus 4ac greater than equal to 0.
B squared minus 4 is equal to 0?
Greater than or equal to 0.
Greater or equal to 0?
Yeah.
If it's greater or equal to 0, what does that mean?
There's a solution for
Okay, so
L of x, basically.
Okay,
you just was thinking of substituting x and y with
okay, so
another
let me
letter.
clarify. Okay, so let me just clarify this, what you're trying to say. This is y equals x squared, and this is y is equal to, and then let's say y equals lx is our tangent line. So in the tangent line, obviously, is going to be something like mx plus n. So we don't know what the line is, but actually in this case, we know the line. The line is actually this guy. So the line is this guy, so let me erase this guy. So L of x is actually 2ax, so 2ax, so 2ax, and then what, minus a squared, we get this. So now you're saying that, first of all, you have to equate the two. So from here, I will solve the system of equations here. So we want to what? So what? So let me put a question mark here. So in this case, left. So left x squared, or you know what, instead of left. So okay, left x squared. You know what, let me just erase just the left here. It's not really left, so let me erase this. So we will, let's say, want x squared is equal to 2ax, and then 2ax, and then minus x squared. Now, if we equate the two y's here, and we set up this equation, what will this equation solve? What will be the solution to this equation? What is the meaning of this equation here? Yeah, now we get a quadratic equation, but what is the meaning of this equation? The solution we get at the end, what will that equal? What does it mean? What question are you solving here when we let x squared equal 2ax minus a squared? What is that we are solving?
I thought I was trying to solve for a, I thought, but I'm not really sure.
If you let these two equations, if you let x squared equals 2ax minus a squared, you know what we're trying to do? We're trying to find the intersection. Because we set these two equal. So are we trying to find the intersection? Is that what the question is? If you let x squared equal to 2ax minus a squared, what we're trying to do is we're trying to find the intersection. Is that what the problem is? Are we trying to find the intersection here? Okay, so are we trying to find the tangent line? So if from here, if you now let d is equal to if d is equal to what? If d is equal to 0, that means we have one point of intersection. So we have one point of intersection, right? And then if d is bigger than 0, then what do we know? then we have what? If d is bigger than 0, then we have 2 points of intersection. 2 intersecting points. But is that what we're trying to show? Here, example 8, what are we trying to show? What we are trying to show is that our tangent line is below the curve. So what are we trying to show here? Now the curve, we said, I call it y equals f of x, and f of x is actually x squared. And the y equals L of x, y equals L of x is actually this guy right here. This guy is L of x right there. So now what is it that we have to show? Now you have to be very clear about this because this is now the heart of the problem. Okay? So this is now the heart of the problem. What is it that we have to show? That's the critical part here. What is it that we have to show? Well, we are trying to show that the line, the tangent line, no matter which tangent line it is, the tangent line is always below the curve. What is it that we have to show? Okay, this is what you have to show. Must show that what? Must show that f of x is what? How do you think do we have, what is the relation between this f of x and L of x? What is it that we have to show here? F of x and L of x. Which value should be higher? So let's say we have a vertical line here. The vertical line. If you look at the vertical line, then note that the point on the curve is this point right here. And the point on this tangent line is over here. And this is our x, any value x here. In order to show that the tangent line is always below the curve, what is it that we have to show? What is it that we have to show what equation is it, what equations we have to show that our tangent line is always below the curve? And this is what you have to show. This right here. If you can show that, that shows that the tangent line is always below the curve. What that really means is pick any value x here, then L of x, and then now we look at L of x and f of x. So this point right here, what is this point? This point is going to be x comma f of x. And what is the point on the line? That point is x comma L of x. And this point right here is x comma L of x. Comma L of x. Now, what is it that we have to show? We have to show that the entire tangent line is actually below the curve. So what is that we have to show? We have to show that f of x is always greater than L of x for any point x. So we don't show this for some x, we have to show that for what? For all x. That is what we have to show. Everybody, do you understand this question here? Okay, class. For problems like example 7 and example 8, let me tell you this. It takes about 3 minutes or 5 minutes to understand the question. The actual answer, the actual solution, takes only a minute. The bulk of the problem is to what? Is to understand the question. Understand the question in such a way that you can format this in a mathematical way. So that is the hard part. So now what I'm going to do is I'm now going to save this, and I'm going to clear this. And why do I clear this without solving that? Because when you go, let's say I just open up the file 0723A. Now if you see the files, a few files down, then there's a file called 0723 example 7. That's the problem where you have to show that the tangent line does not pass through 1, 3. so here it is. There's the solution right there. Okay, so now what I'm going to do is I'm going to just close it. And then example 8, you have to show the line is below that curve. And so there's the solution right there. So what I recommend you to do is example 7 and example 8, why don't you try to do the rest of it on your own? And then, so think about it, because the problem is to help you how to think. That's that's what you have to learn here. Because even if you just look at the solution example 7 and 8, what's going to happen on the test? Well, I'll give you something else. It doesn't help you. But if you just learn the solution to example 7 and memorize it, that does not help you. So you have to understand it. So I want you to look at the question again, and I gave you all the hints. And now with the hints, try to solve it. And if you cannot do it, then you can look it up. You can look up example 7. But if you look at the solution, let me tell you, you are wasting examples. Okay? So I don't want you to waste any of these examples here. So think about it, and think about it. I don't know, you may have to think for about 10 minutes or so, and then try to actually do it. But I have given you enough hints. But example 7, example 8, on those two files, the question is completely solved to the end. Okay? So if you have a question and you want to know what the solution looks like, then you can open up. But again, before you open them up, I want you to do the problems. Is that clear? Capish? Entiende? All right? Right. So I want you to try those problems on your own. The problems like example 7, example 8, the calculus are super simple, but you have to understand them. Understanding the problem is the key. And understanding means not only just understanding the problem, but knowing what to show. That is formulating into a mathematical problem. That is the hard part. So when it comes to math, in some ways the hard part is this is not a word problem, but obviously the problem is in words. So when you have a problem in words, converting that into a mathematical form, converting to a mathematical problem, the fully mathematical problem with no words, that is the hard part. So that's what we call formulating the problem. So if you know how to formulate, if you know what to show, then that's the hard part. The actual showing, it only takes a minute. It only takes a minute. Okay? It only takes a few lines. That's it. So there's not much. Again, the hard part is for you to understand and know what to prove. Okay? And this is now real mathematics here. The real mathematics is you know what to do. Once you know what to do, then the actual doing is very simple. But I want you to learn how to think. Okay? Not just look up a solution. Okay? That's the easy part. But anyway, solutions are already provided here. So that's that, okay? And then we did the common tangent problem last time. The tangent line which is common to two curves. Okay, and so we have done that. Okay, now let's look up section 2.4. 2.4a, we have 2.4a, and I have 4 files here. The first one is 0.0724a. So that will be the first file. So let's look at this. Now we get into trigonometry. So let's look it up. Okay. Section 2.4, derivative of trig functions. And the first theorem is actually quite easy. So we assume that the cosine functions and the sine functions, well, I should have put a space there, but I guess there's no space. But anyways, limit of, limit of sine theta, where theta approaching 0 is 0. And limit of cosine theta, theta approaching 0 is 1. Now in this case, this is not so interesting. This theorem is not so interesting because what is sine 0? Yeah, we kind of know what sine 0 is. Sine 0, 0 radians is actually 0. Then what is cosine 0? Cosine 0? Cosine 0. Would anybody know what cosine 0 is? Yeah, you should know this from the last quiz, right? Cosine 0 is 1. And also note that we assume that y is equal to cosine x. Cosine x squared is continuous. Continuous. And the y cosine x is also continuous. So those are the things we assume. Okay? Even though we didn't prove that, we will assume that. Continuous. I'll just write cont. Okay? Cont. I'll just say cont for continuous. So that, and so now theorem part one, the very first theorem, actually there's not much going on there. So that one, yeah, there's no mystery there. Now, here the question is now this: the derivative of trig functions. So what we now trying to do here is the derivative of the trig. So we want to find the derivative of sine theta with respect to theta. So sine x with respect to x. We want to find the derivative of sine function, sine x. So before we do that, we need to have one theorem. And the theorem is this right here. So limit of sine theta over theta as theta approaching 0 is 1. Okay? So what is this theorem here? Now, first of all, we have a limit here. What is this limit of sine theta over theta as theta approaching 0? What is that? So for any kind of limit, now, class, for any kind of limit, when you have a limit like this, limit of sine theta over theta, theta approaching 0, what is the first thing you have to do? We note that the sine theta is a continuous function. Yeah, sine theta is a continuous function. So let me write this down again. So we have a limit. So this is a limit here. And the limit of what? Sine theta. Sine theta. And note that sine theta is a continuous function. And then this theta is also a continuous function. So now it says here x is approaching 0. So in order to evaluate this limit here, what is the first thing you have to do? How do you evaluate limits? Now we go back to chapter 1. So when you have a limit problem like this, how do we evaluate the limit? What is the first step? Can you tell me the first step of finding the limit? Any kind of limit problem, what is the first thing you do? For any kind of limit, for any limit problem, what do we do first? What do we do first? What do we do first? What do you do first here? Can someone tell me? For any limit problem, what is it that we do first? Now, note that this cosine theta is a continuous function, and this theta is also a continuous function. So in this class, we will assume that they are continuous. And of course, you all even know their graphs as well from trigonometry. Again, this section 2.4, you need to know some trigonometry, okay? Now here, in this class, I am not going to give you problems just to test your trigonometry, but I will be testing you on trigonometry for things we need on this chapter. Okay? So by the way, the sine theta and cosine theta does not show up just in section 2.4, but when you get into section 2 chapter 3, chapter 4, chapter 5, these sines and cosines will keep on showing up. So from this point on, you will see sine theta, cosine theta, or tangent theta, and the other trig functions. You will see them throughout. Okay? So the trig is not just for this section. It is going to show up in every section, every chapter from here on. Okay, so what is that we have to do here? We have a limit problem, and we note that the sine theta and theta are continuous functions separately. And so what? I wrote down x is approaching 0, and that is a big mistake. So I should not say theta equals to x. I should say theta is equal to theta is approaching 0. So theta is approaching 0. So for any angle, we somehow the variable we use in common is theta. Of course, it can also be written with x2, which is very common. And soon, actually, I will be switching from theta to x. So we write it this way. Limit x equals limit as x approaching 0, and the equation is now sine x over x. You will see soon the problem in x instead of theta. Okay? So whether we write x or theta, they're exactly the same problem. As long as the three letters match, they're exactly the same problem. So how do you evaluate limit sine x over x as x approaching theta? How do we evaluate it? For any kind of limit problem, what do we do first? Can you tell me? Now this here, how about this? If we let x equals 0, what do we get? Then we get 0 over 0. Oh, so we do get 0 over 0. 0 over 0? What is that? That's an indeterminate form. That's an indeterminate form. That means in this case, we cannot plug it in. It becomes 0 over 0. So the question is, what is the sine x over x? And by the way, this x right here, or this theta right here, this angle is in radians. Okay? Angles are measured in angles measured in radians. Measured in radians. Not in degrees. Of course, we can always come up with formulas where the angle will show up in degrees, but the angle measures will be in radians. So, for example, when you plug in the value, let's say, for example, what is the value? So we can create a chart like this. So let me create a chart, x here, and x here, and we have sine x over x. Okay, or theta, doesn't really matter whether you call x or theta. And now we are letting this x to approach 0. So we are letting this x approach 0. So let's plug in here. Let's approach 0 here. Now in this case, what do we plug in? Let's say we plug in 10 degrees. What is 10 degrees in radian? 10 degrees. What is that in radian? What is that? 10 degrees in radian? 10 degrees in radian. Pi radian is what? 180 degrees. So it looks like this will be 100 pi over 18. 18 radian. So let me write radian here. It will be radian. So in this case, what happens if we substitute pi over 8? Pi over 18. If substitute pi over 18, then what we end up getting is sine of pi over 18. The sine of pi over 18. And the important thing is that over, this is pi over 18, and then what? Over what? This is now pi over 18. Now note that when you plug in these values here, this pi over 18, now what is the value of pi over 18? Pi over 18, what is this numerically? We have a value. You know what? Let me just use my own calculator here. What is pi over 18? Pi is about 3.141, and then divide by what? 1.16, and then divide by what? Divide by 18. 18, that will be about 0.745. This is about 0.745. So about this one here is about, let me write this down. This is about 0.1745 radian. That's about 0.1745 radian. So basically what I'm saying is this. So when you plug in a value for x here and then evaluate it, we get this. So note that this is sine of pi over 18 radian over pi over 18. So when you put a pi over 18 there, that number right here, what is it? That number right there is about 0.1745. It is not 10. So we don't plug in 10. If you plug in 10 here, then this limit does not go to 1. It will go to something else. Okay? So make sure that you understand this. Again, case is measured in radians throughout calculus. So when you deal with the calculus of trigonometry, all the angles are measured in radians, and all the formulas are based on radian units. If you don't put radian, now here, whether you call this guy 10 degrees or pi raised to radian, you get the same value. But this guy extra here is not so. So plugging a 10 here is not the same as plugging in pi raised 10. Pi raised 10 numerically is about 0.1745. So here, you're substituting the value. So this value right here is about 0.1745. It is not 10. So there's a big difference between the degrees and radians here. So plug in pi raised 10, and then if you plug that in, then you get this right here, which is actually 10 degrees. So when you plug in into this x into what? Into the expression sine to x, you have to plug in the value in radians. And this guy pi raised 10 will make a difference. Again, putting a 10 here is not the same as putting pi raised 10. Because pi raised 10 radians is about 0.1745. It's actually a different number. It's not 10. It should be about 0.1715. And now, you want to make this approach 0 here. So next thing you want to plug in, maybe how about if you now plug in pi over 180 degrees? Well, pi over 180, which is 1 degree. And when you take this limit here, what happens? Will it approach some number? And the question is, what number is this going to approach? Will it approach any number? And actually, it will. Okay, it will. Okay, so now, how do we do this here? Now, this is a new kind of limit. It involves trig. So now, how do you prove this? So sector area. Okay, now, this is something all of you need to know here. Sector area. All of you know the sector area formula. How about this? Let me draw a sector. This kind of a shape right here is called a sector. Then sector, like this. And then this angle right here, let's call this guy theta. Okay? And if we call this guy R, now, do you know the formula? What is and this area is the area, A is the area of this sector. And this kind of a shape, we call this a sector. So let me write sector here. Sector is a term which is used in circle geometry. Now, the part of geometry you need is what? You know what? You need to know trigonometry, that's right. So you not only need to know geometry, but you also need to know trigonometry. So I'm not going to spend too much time here. But this kind of a shape, which is like a pizza slice, I mean the usual pizza slice, if you go to any pizza store, of course these days some pizzas are cut in a rectangle form, right? In rectangle. Yeah, that's what they do. But anyway, the traditional way of cutting the pizza is in the shape of sectors. You cut into these pizza slices, and that shape is called a sector. So sector is a part of a circle, in the shape which is bordered by two radius and the arc of the circle. So again, sector is a shape which is bounded by what? Bounded by the circumference, that is the arc length, that is the circle, part of the boundary of the sector is the circle, and then the two radii, or two radii. This kind of a shape is called a sector. It's basically what I call a pizza slice sector. Now, what is the sector area? What is the formula for the area of a sector? Again, I'm not sure what you did in your trigonometry class, but you must have seen this formula. And this is basically what? A is equal to, what is the area of the sector? Is equal to, what? Is equal to half times r squared theta. I don't know, did you all learn this in your trigonometry class? And the theta, where theta must be radians. Where theta is in radian units. So let me write this down. The theta, where where theta is in what? Where theta is in what? Where theta is in radian units. So in order to find this area of the sector, the area is equal to half r squared theta. And the theta must be in radian units. If that theta is 30 degrees, then you cannot put in 30 there. You must put in pi over 6. So you have to know the radian units, and that's the area formula. Again, if you do not know this, formula here, the sector area, you have to look up zero notes. Yeah. So m0. So what is okay?
Yeah. So for sorry,
what is it?
For sine theta over theta, is that just for the sine functions or also for the cosine?
You mean this limit formula?
Yes.
The limit sine theta over theta is theta approaching 0. Whether this is only for sine function?
Yes.
Yeah, this is only for sine function.
Oh.
If you put a cosine theta instead of theta, that will be a different limit. If you put something else, then that's a different thing. So this is just one function, one limit problem, but it turns out that, as we all know, this limit problem or this limit form right here, this is very important. It turns out that this is the only one we need. So when it comes to limit of trig functions, again, when it comes to limit of functions which involve trig functions, then this is the only limit formula you need to know. And all the other formulas, all the other problems will use this. So this is only one, it's only for sine. It's only for sine theta over theta, theta equals 0. But this one limit formula is the only limit formula you need to know. All right. So anyway, so it's only for sine. It's only for this particular limit. This is just one particular limit, but we call this a theorem. Why? Because this theorem is very, very important. So now here I'm in the process of trying to prove this. So here I'm drawing a diagram. So now, before I draw a diagram, you need to know the formula for the sector area. The sector area formula is this guy right here. This is the sector area formula. This is called the sector area formula. The sector area is equal to half r squared theta. Okay, that's theta. And so again, you know what? This is not a trigonometry class, so I don't think I can spend time on this guy. If you don't know this, please study. Please study the proof of this sector area formula, which is actually quite simple. Okay, but everything I do will cost time. So, and this is trigonometry. So I cannot go back and do all that trigonometry, okay? In my pre-calculus class, in my trigonometry class, of course, I spend quite some time on these here, okay? But here, you know what? This is calculus now. So please, you are on your own. You have to study. But I don't, you don't have to know the entire trigonometry, but quite a few stuff you need to know, okay? So now, in order to do this here, what we do is we actually draw a diagram. So let's say we have a sector, and we have a theta here. Okay? And we have what? We have and we have this. Now in this case, why don't we let this? We have a diagram here, and so why don't we let this theta? Now we let this theta between 0 and pi over 2. So theta is between 0 and 90 degrees. And then now we are going to draw. I'm going to let the radius be 1. So right now you may question why I draw this picture, why this diagram. But this diagram will work. That's why. So let's say we have a diagram like this. So we have a sector with radius 1, radii 1, and then the central angle is theta, and we assume the theta is between 0 and pi over 2. It is a positive angle between 0 and 90 degrees. Now, what do we have here? You know what? After this, actually, so you know what? Let me change the file here. There's a file here, next file. So what I'm going to do is I just saved this. I took a screenshot, and by the way, I don't know whether I told you this, but all the screenshots can be found under modules. If you go to a menu called modules, and that's the place where we find the screenshots in the best, or in an organized manner. If you go to files where we find your notes, I noticed that all the files all the screenshots are in the bottom, and all the files are kind of mixed up. So I decided not to organize it over there, but the same files, the same screenshots can be found under modules. So let me write this down. Okay? So again, all the what is it? All notes, all screenshots, okay, can be found. All the screenshots is found under the menu what? Modules. Okay? And when you go to modules, you know what? The only thing you find there are screenshots. Okay? So that's where I decide where I put the screenshots. Okay? Under files, you will find the same screenshots, but they're not organized. Okay? So I decided not to organize over there. So just go to modules and you'll find all the screenshots. Okay? I put the screenshots usually immediately after the pass it over. Okay? And they're organized by dates. Again, organized by dates. So when you look at the file number, you know what date it is from. So you know, okay, you can kind of look it up. But each screenshot do not have a title. They're only organized by date. A 4-digit date. Like today is what? January 20. If it's January 20, then it will say like this. Let's say SS, yeah. It will say, let's say, how about this? SS 0120. And then SS 0120.
No.
Then this is actually a screenshot.
Why?
Screenshot for
My class.
screenshots on what, January 20. Okay. So the screenshot today will
He's
be
adorable.
SS0120, and then there's the file 1, and then 2, 3, 4, and then they go by numbers. So all the screenshot file numbers and names are named in a chronological way, by dates and by the chronology. So screenshot 1, 2, 3, 4, and then okay. So that's in case you didn't know, find the screenshot. That's where you can find it. Okay.
Nobody knows.
So much on that. So now maybe I should erase this. Okay.
Yeah.
Now here's diagram. Now what I'll do is I'm going to save this now, and then I'm going to clear all this. Why? Because
congratulations, man! You have a beautiful baby
yeah, one on the
boy.
file here.
Now,
The
you
second
just
one,
need to cut the most sensitive
2.4
part off the beer
0.724
boy's
E.
penis.
I'm recording my
Differentiation
class.
of sine. So here,
Oh yeah. Just do it. It's fine.
when you look it up,
Sorry.
it is basically the same file. Oh, did I say 3.4 here? Yeah, that's I didn't change that. It should be 2.4. If that's a typo. But anyway, if you look at this file, you actually have a proof here. Okay, the proof of that theorem is actually spelled out. But the only thing missing on this proof is actually the diagram. So what I'll do is I'm going to draw the diagram, okay, so you understand the proof. So the diagram is actually over here. So we have a sector.
Actually, there's these kids down below and I flew down and I picked them up and I tried to
This is
suck
data.
them like a Dementor.
Weird.
That's lucid.
We didn't
data.
do
I
that.
tried.
We didn't do that.
And this is what, 1. So let's say the radius is 1 here.
Then I woke up.
And so what we do is I'm now going to from here.
People
I'm now going to what? I'm now going to write a perpendicular projection onto the horizontal line right here. So this is a 90 degree angle right here. And then what I'm going to do is I'm going to actually draw a line here, this point right here to this point right here. So let me draw a line. And now I name these points. OAB, let me see. OAB, which one is O? So O is this guy right here. Center of this point right here, the P, which is really the center of the circle. That's where the two radii meet. That point is called O. And then this point right here, I think I call this guy A.
It's funny how he can like convince himself it's something to get, not like he's not like, oh, it's just your hand. He's like, I gotta get it.
And then there's the point P. Oh yeah, P. You know what? we have to
Again,
extend
There's
this point.
definitely a bunch of baby worms crawling out of a hole.
Why do I not, use a different color? How about if I use let's say
Definitely a
green?
bird
And the
wing
green,
that's
I'm just going to
flapping
extend
around.
this.
I'll show you a big
And
worm.
here, I just extend this line right here, like this.
Oh my God.
And then I'm now going to draw a line like this. A vertical line. Where once again, this is also right angle. And at this point right here, call this guy T. So again, why do we draw this diagram? Because this diagram works somehow. Okay? So that's where we are getting all these inequalities here. Okay? So this is the starting point. So somehow we draw this diagram and this diagram actually works. So let's say we have a diagram like this. And now we have this. So now we go back to the same thing. We're trying to prove this limit theorem here. And then the case when theta is between pi over 2 and 0 and pi over 2. So this theta right here, we assume that this theta right here is between 0 and pi over 2. This theta is between 0 and 90 degrees. So if theta is between 0 and 90 degrees, then we are going to get a diagram like this. When theta is bigger than 90, then we don't get a diagram like this. When theta is negative, we don't get a diagram like this. So this diagram will look like this if theta is between 0 and 90. So that's what that is. And then mark all these points here. Mark 0, A, and B, and T. And so that's already marked here. Okay, I marked there. And so what is this 0? The origin is actually 0, 0. That's the exact coordinates of this. So if you like, we are actually putting an x-axis here, and this is our y-axis here. This triangle and the sector is actually what lies on the xy axis. So that's the y-axis here. Okay, so what is O? O is 0, 0. What is A? A is 1, 0. Because we assume that the radius of the sector is 1. And then what is B? The B, this point right here, yes, this point. This point is cosine theta, sine theta. Now again, I'm not sure how much we're going to remember, but this is actually a definition of cosine theta and sine theta. Again, you have to review this. Okay? This point B is called is the point cosine theta, sine theta. When you have a unit circle like this, the circle with radius 1 with center at the origin, go like this. And then we have that point right there. That point B. This theta is what we call the standard angle. And this point is now cosine theta, sine theta. Again, you know what? I don't know how much I have to say, but please review your trigonometry. Review and study trigonometry. Again, when I ask you to review and study trigonometry, it is not just the formulas, but you need to know the definition of sine and cosine and how sine theta and cosine theta are defined. And such things as the arc, the sector area formulas, they're very, very basic. Very basic things and definitions, you have to know them, all right? It's not just memorizing some formulas there, like sine of minus 8 and minus x is equal to minus sine x, and cosine of minus x is equal to cosine x. Yeah, there are a lot of formulas like that, sure. But it's not just memorizing the formulas. The key is to understand the definitions. Make sure that you review your definitions and the very basic formulas first before you move on to memorizing formulas, all right? So the definition of sine and cosine, this is actually how the sine theta and cosine theta is defined. Okay, so anyway, and then t, what is the t right there? If you look at the t, what is the x coordinate? The x coordinate of the t is 1, as you can see, because the point A is 1, 0. The radius of this arc sector is 1. So the t is 1, and then now what is the y coordinate? The y coordinate happens to be tangent theta, because if you look at the triangle there, what is tangent theta? What's tangent theta? What is tangent theta? The tangent theta is equal to this. Tangent theta, this is tangent theta. The tangent theta is equal to, see this triangle is right here. So when you look at this triangle right here like this is theta. and this is 1, okay? And why do I call this guy W? Okay? This point right here, we call that, why do we call this guy 1 comma W? 1 comma W. Then now, how do you get that W? Well, what is tangent theta? The tangent theta is equal to, tangent function by trigonometric triangle definition equals like this. So that will be what? W over 1. I don't know. Do you remember this guy? And so what is W? W is tangent theta right there. So this W right here is tangent theta. So that's why we have this tangent theta right there. This is 1 comma tangent theta. This T is 1 comma tangent theta. The tangent theta is what? Is AT over OA.
Did you say it was?
In our case, OA is 1, and AT is that value, the y point of the T. Anyway, that's the diagram we need. And now, here, if you on this proof here, the argument starts with this guy right here.
So what did the doctor
This is the
say?
first guy you have to understand. You have to understand where this guy is coming from. This limit formula, the argument is starting from this inequality right here. And so this inequality, it seems like it's coming from nowhere. It is coming from nowhere. It is actually coming from this diagram. So let's try to figure out what this inequality is. The inequality says the m by the m stands for measurement. So when you see this notation right here, what does it mean? What is m? And then parentheses triangle OAB. What this means, this is the area of the triangle OAB. Again, this m right here, this part is m of triangle OAB. What does it mean?
Did you take your meds
What
last
does it
night?
represent? What does it mean? The m of OAB,
Yeah, see, it's
this is
amazing
referring
what's
to
over-the-counter
the
thing
area of the
schedule.
triangle OAB. Okay, let me write this down. So what is this equal to?
I think you weren't getting
This
enough
is equal
sleep.
to the area of triangle
14.
OAB.
Okay, so that's all they said. Then inhaler. Is it a what kind of inhaler is it?
Right?
Alright, well, what
You know
about
what?
vitamin D?
Let me chop it up. Yeah, let me just write like this.
Is it called in?
So the MOA, the triangle OAB, refers to
Yeah, just tell them
the
to fill out your
triangle
prescriptions and I'll
OAB.
go pick them up.
If
We
you
call
look
it the
at the
Santa Monica
diagram,
one,
where
and I
is the
put the phone
triangle
number on
OAB?
your little note.
The triangle OAB is this guy right here. So the triangle OAB is over here. Is this guy here.
Beverly.
Triangle
CS?
OAB is this guy.
They should pay for it at end. No, I'm fine.
Again, the triangle OAB.
I'm okay.
Now what is the next guy? Now this is less than, it says the triangle, the area of the triangle OAB is
Same
less
thing.
than the area of the
Same thing,
sector OAB. Now what is that?
Mm-hmm.
The sector OAB is now is this guy now. It includes this part. The part which is sticking out.
I just got out of the shower.
It's this area more. If you have that tiny area there, then that is now the area of the sector OAB. So the first one is the triangle OAB. The second guy is the sector OAB. And then now the third one, that is going to be less than the triangle OAT. Or OAT is this big triangle now. So that is going to be bigger, of course. Much bigger. So that's where we get that formula. So if you look at that formula, so what is the area of this triangle OAB? Triangle OAB is a triangle. It's half times base times height. Half times base is 1, and the height is sine theta. Sine theta, why sine theta? Because B is cosine theta, comma sine theta. So this height is sine theta. So that's where that is coming from. And then what is sector OAB? What is the area of the sector OAB? That will be half times r squared theta. So that's half times 1 squared, the radius is 1, and then theta is theta right there. And then, now what is the area of the triangle OAT? OAT is half times base times height, half times 1. 1 is the base, and then times height is tangent theta. So that's where you get that inequality. And then when you multiply all three sides by 2 over sine theta, You multiply all three sides by this multiply all three sides by 2 over sine theta, then you get we get this equation right here. You get this equation. And then ultimately, on this equation here, what do? You now take the limit. See, we have this equation right here. Same equation. And then what do? You attach a limit here, and then attach a limit here, and attach a limit here. So when you attach a limit here, the left side becomes 1, because you have limit 1, theta is equal to 0 is 1. There's no theta. And if you look at the right side, you get limit of 1 over cosine theta. Theta is equal to 0. So cosine 0 is 1. So you get a 1 here. Get a 1 here. And then the middle limit is over here. This guy is now this limit right here. Or that's the limit which we're trying to find, right? That's the limit of theta over sine theta. And actually it's a reciprocal. Here we have sine theta over theta, but this is theta over sine theta. But you know what? We will get that limit. Same thing. This limit is 1, that limit is 1. All of these limits will be 1. So this is the limit of theta over sine theta, theta approaching 0, and that's stuck between 1 and 1. So the conclusion is that this limit will be 1. Right here. That's where we get that limit, right there. So you know what? Probably if your trigonometry is weak, then you might have a hard time, going through all this.
It's a deliberate,
but make sure that you study this. In the proof,
decision to destroy
many
the economy
techniques are involved.
and blame it on
Many
them.
techniques are involved here, and therefore,
look at
I
all
want
this
you to
mess that
study
they
this
created.
So, if the limit of theta over sine theta is 1, then how is that? You know what? I actually did not prove this guy. Actually, I should have included one more step here, and the step step is this. So what is the limit of? What is actually this is what I need. So let me now add the step here. And so what we need is the final step. So let me write down the final step. The final step is actually not written there. So let me add this final step. The final step is this. So therefore, what is the limit of this original problem here? The limit of this original problem, the limit of sine theta over theta. So this is the limit of sine theta over theta. Sine theta over theta, where theta is approaching 0. What is this limit here? Now we have found that the limit of theta over sine theta is 1. So therefore, what is it equal to? This is actually equal to the limit. The limit of what? The limit of 1 over theta over sine theta.
Yeah, good job, good job.
Because this is an indeterminate form. Note that this is 0 over 0 form, so we can't plug it in. So we can actually change this to this form. So write that sine theta over theta as 1 over theta over sine theta like this. And then theta is approaching 0. Is that true? Yeah, it is true. Of course, here we are saying that theta is not 0. When theta is approaching 0, theta is not 0. So we can do this. The denominator is therefore not 0. We just want to know what the limit is. But we are not letting the theta be 0. And now, this is the limit of a quotient. Now the question is, now let me put a big question mark here. This big question mark. Now, would this be the same as 1 over this? Can you split the limit? Can you just apply the limit to the denominator separately? Can you do this? So here, I put a big question mark. So right here, theta is approaching what? 0. We get this. The question is, will this limit exist? And so here, the big question is, we have to put a big question mark right here. This split may or may not work. There's a question mark. So I'm going to put a big question mark here, and let me put the big equal sign right here. Is an equal sign. This equal will go through if the final limit will not be a problem. But now if you look at this, what is this limit here? this is actually
Can you
equal
go
to
for a
1
walk?
over, and then this whole thing right here, this is now what? 1. Because that's what we found right here.
I swear they like this
So this
last
is actually
episode
equal
before
to
it so they
1.
could see this one actress's.
So even though the limit is a 0 over 0 form, by the way, to find this limit here, to guide this limit,
she
we
has
cannot
really
apply
giant
any of the
boobs,
techniques
and
we
they're
have
like,
studied
we
so
need
far.
to do some sex
The
with
technique
her
in
now.
chapter 1, it doesn't apply
Which one?
because we now have a trig function.
I don't know her name in real life.
Okay.
Cassie.
So as theta is approaching 0, what they're saying is the theta and the sine theta, the ratio is 1. So what that really means is as theta is approaching 1, as theta is approaching 0, what happens to the theta and the sine theta? They almost become the same value. So now let me show you what that means. Let me go to decimals at this point. I took a screenshot there,
Is this box
and I'm
growing?
going to go to decimals here. So let me just go to decimals and see what
Is
it
this
is.
box growing?
Okay, so what is it?
Yeah.
Decimals graphing. We have this right here. Oh yeah, we have this. Now I typed in all this here for tangent lines. Let me see. You know what? Let me just go to another decimals. I don't
Okay,
want
I'm
to
gonna be working
mess
from
up.
home.
Okay, am I sharing this decimals here? Okay, there's no very good shit.
It's really nice to
So
actually
here,
have an office
y
that I
equal
don't have
to,
be at
let's say,
every
sine
day.
x. Oops. Sine x. By the
And
way, when
it's
you
kinda
type in y for
perfect 'cause,
sine x, this is obviously, this is what? This is
office
measured, x is actually
is-
measured in what? In radians. This x is measured in radians.
like mostly very convenient. You don't have to take a stinky train. But it's only 3
So note
stops,
that this
and
is a
then
sine
it's
graph.
just like
The red graph is a sine
a
graph.
pretty easy
And I would
walk.
like to let you know that the sine x is
To the
actually
office.
measured in what? In radians. So what do I mean by that? Because when you look at the sine graph here, and let's look at the peak. Let's look at the peak here. If you look at this peak here, right here, let's say some point over here, that looks like a peak. And this point, if you look at this here, where is that? Well, that's between 1 and 2.
fancy boba place.
Isn't sine of 90 degrees equal to 1? Yeah, sine of 90 degrees is 1, but the x value here at this point is not 90. It's between 1 and 2. So what is that 1 and 2? What value is that? And that actually happens to be pi over what?
Sorry for
Pi over
the
2.
car.
Pi over 2 is 90 degrees.
Okay, I knew that
So
was
what
gonna
is the
happen.
numerical value of this pi over 2?
I shouldn't have
Pi
met
is about
you.
3.14. So pi is
That's
again is
not
about
normal,
3.14. So pi over 2 is going to be about
Yeah,
about
but I knew that was
That
gonna
will be
happen.
about
I don't know why.
1.57.
I thought you would remember, I guess.
1.57. That's what 1.57. So note that when x is about 1.57, the y equals 1. So x is not 90 here. It's not the point 90, 1. It's actually about pi over 2, 1. So what I'm letting you know is all the graphs, the default unit is radians. It's not degrees. Okay? And then now I'm comparing that to y plus x. When you look at the graph y plus x, you get this. So what you do notice that as x is approaching 0, both are heading to 0. Both are heading to 0, but the important thing is that as we approach 0 along the sine curve, and as we approach 0 from the line y plus x, they almost become the same value. They're both going to 0, but as you can see this part right here, the sine x and the x, their value becomes almost the same. That's what they're saying. And so when they're almost the same, what that means is, when x is what? When x is close to 0, when x is close to 0, then what can you conclude? What we can conclude is that sine x and x, the ratio is about 1. You know, maybe I should write this. Maybe I should write this here. How about this? Maybe I should write this instead. And then this sine x, this is about x. Sine x and x almost have the same value, even though they're both small, but it's almost the same. So what that really means is sine x over x actually is very close to 1. That is when you look at the graph. Now let me take a screen. This. How about this? Excuse me, I'm getting a phone call here. Phone call. Okay. So, how about if I graph the equation y plus tangent x? Oh, y plus tangent is this guy. Now, when you look at the graph of tangent x, now at near 0, they almost coincide. So what you see is that when x is close to 0, well, do you know what you see? What we see is this. What we see is annotate here, and now this one here is almost going to be when x is close to 0, sine x is close to x, but x is also close to what? Tangent x as well, as you will see. Now, why is sine x close to tangent x when x is close to 0? That's because tangent x is actually sine x over cosine x. Sine x over cosine x. And when x is close to 0, what is cosine x? See this cosine x right here? This cosine x? This almost becomes 1. When x is close to 0, cosine x is almost 1. And when cosine x is almost 1, then that leaves sine x. So when x is close to 0, sine x and tangent x, they all become about the same value. They all go to 0, yeah. Even though they're tiny, the ratios will get close to 1. So they almost become the same value. Yeah. Okay. So that's what the graph shows. In fact, this y equals x. So y equals x, by the way, here. So let me write this down. Basically, we can say like this: tangent line to y equals tangent x, y equals sine x at x equals 0. What is that tangent line? What is the tangent line to y equals what? Tangent x at x equals 0. You know what it is? What is the tangent line to the curve y equals sine x at x equals 0? What is that? The tangent line to the curve y equals sine x at x equals 0 is actually what? Is actually y plus x. Y is equal to x. What is the tangent line to the curve y equals tangent x at x equals 0? Also y plus x. So y equals x turns out to be the tangent line to the curve y plus sine x, and y plus tangent x at x equals 0. So when you look at the graph here, it kind of makes sense. Even though they all become the same, the ratio is about 1. In other words, their values almost become the same. Okay? Now let me also show you this graph right here. Let me also show you this graph. So what I'm going to do is I'm going to now show this graph here. How about if I erase everything? Should I erase everything? Yeah, let me now save. And I'm going to clear all this. And now, let me now graph this guy. Y equals sine x over x. This is the graph of y equals what? This is the graph of y equals sine x over x. It kind of look like this, okay? But anyway, right now, we will be focusing on what? Focusing on x equals 0 at this point here. So this is how the graph looks like. But when you look at this here, you see we have a problem here. It looks like the curve is everything looks nice. And we don't see any problem at x equals 0. But you know the actual graph is? The actual graph should be like this. This is at 1 here. That we should have an open dot here. Why? Because this y plus sine x over x is what? Y plus sine of x, sine x over x. What is this here? This is undefined. Well, we're undefined when x equals 0. It's actually undefined when x equals 0. But when you look at the graph, it doesn't show that. So why is it that why does it show as if it's a continuous function like this? And that's because y equals sine x over x is undefined x equals 0. It has a what? Has a removable discontinuity. Discontinuous at x equals 0. But this is a removable discontinuity. Removable discontinuity. This comes at x equals 0. So So even though the function is not defined, it has a two-sided limit. It's a very interesting function. Once again, y plus sine x over x is not continuous at x equals 0, therefore it is discontinuous. But that discontinuity is a removable discontinuity. If we just fill that point in, then it becomes continuous. So it's actually a very nice function. Okay. Again, when you graph it, it does show that. It shows as if it's a nice function, and then it doesn't break down. It looks like a continuous function, but it's actually what? Once again, when you raise it, this is how it shows. It looks like it is a continuous function, even though it's not. But again, the reason why we do that is because it's a removable discontinuity. If we just fill in that point, then it becomes continuous. Any questions on this? Any questions here? So let me just, where is it? Annotate. So what is this? Okay, all right. Let me just save this, and I guess and then we'll have to say goodbye to this website. Okay, so okay, that's it. So you can play around with these, these graphing calculators to help you understand what's going on. But that's what it is. Okay, so let me now clear all this. Then let's go back to files. Again, those of you who trigonometry is weak, make sure you review your trigonometry and please study this proof right here. Many things are involved here. And especially, by the way, when you look at this problem here, when you look at this proof, we start with this case right here. We started with this case when theta is bigger than between 0 and 5 over 2. And then we get the result right here. Sorry, not that one. That's the wrong one. We get the result right here. And then from this inequality, which is right here, we actually attach the limit. Theta is approaching 0, and the limit theta is approaching 0, and theta is approaching 0. This attaches limits to all three sides. This is what we call the squeeze theorem. This is what we call the squeeze theorem. Squeeze theorem, or it's also called the sandwich theorem. Sandwich, they have two names, either the squeeze theorem or the sandwich theorem. The squeeze theorem is the more common name, but some textbooks some teachers they call it sandwich theorem. So anyway, they are both the same thing. And this is actually something we skipped already. It wasn't actually in chapter 1. You look up, was it chapter 1? Let me see. Let me open up. Let me check where this was. Where's my chapter notes here? The chapter notes. Yeah. Let me open up my chapter notes here. A section of chapter 1, and this was actually mentioned, but I didn't go over, and that was in section 1.6a. On our class notes, section what? Several class notes. Section 1.6a. On section of 1.6a. Okay. If you go back to section 1.6a notes, I think it's the second. Is this the second page? Yeah, it is the second page. Second page of this notes, you will see the sandwich theorem or the squeeze theorem. Okay. So anyway, I want to look at that right now because at that time I skipped it. Okay. But now it's covered. So what is the sandwich theorem here? Basically, it says here when you have an inequality, you can attach a limit. But now the thing is, why do we have this second case right here? Why do we have the second case? The question is, why do we have this case? Why not go from here to here directly? So we have 1, and then less than, and then we have theta over, sine theta, and then this is going to be less than, and then 1 over cosine theta. This is what we had, right? Now, and then what we're going to do is, because we want to evaluate the limit, we want to get the limit of this guy and the middle guy, what we do is we put the limit here. So let me now write, maybe I'll write this in blue. We now put the limit here, the limit as theta is approaching 0. And then the limit of theta approaching 0. The limit theta is approaching 0. And then we now put the limit of theta approaching 0 right here. Oops. Sorry, another jump call. So we have the limit here, limit here, limit here. So theta approaching 0. Why could we not attach this limit? Why could we not go from the first case, to this limit right here, to the conclusion? We can get to this guy to here. But the question is, what is this? What is this right here? Why do we need this guy? That's the question. Well, what is this? What is this in the middle? So you put the limit here, and will that work? Well, you cannot go from here to here. From here to here, we cannot go. We can't do that. No, not ready. To go from here to here, it's not ready. This is not ready. Why are we not ready? And the other ones, no. Okay? We cannot go from there to there directly. Why not? You know why? Because it says here, this inequality is only true when what? The inequality is only true when theta is between what? Between pi over 2 to pi. So theta is only true between what? Theta is between, this statement is true only when theta is between 0 and pi over 2, namely when theta is bigger than 0. But in order to attach this limit, what must be true? Theta, this inequality must be true when theta is a little bit bigger than 0, but also when theta is less than 0. So we cannot go from there to there. So this middle step shows that if theta is now less than 0, slightly less than 0, then we end up getting the same inequality. So you have to kind of understand the logic, why we are doing this. What are these cases? So that we can ultimately, We can ultimately attach this limit right here. So this one is no, we cannot go from here directly. But from here to here, if you want to go to this limit, we can only attach the limit as what? Limit as theta is approaching what? Theta is approaching 0 plus. This we can do. Because this statement right here, this inequality, is true when theta is bigger than 0. So when theta is bigger than 0, attach this limit. But we don't want this limit. We want the two-side limit. That's why we had to go through this. Okay, but anyway, sit down and try to learn as much as possible from the proof. Even though I will not ask you the proof, but the proof involves many techniques which you need to know. Is that clear? So when you solve problems, you need many of the techniques which use right here. So this is like solving a problem as well. So that's why you want to learn how this proof works. And you have to understand why, and then you also have to understand the logic of this proof. The logic of this proof and how this entire theorem works. Okay? So now we get this. So I'm now going to save this, and now we need to clear this. And so study that proof. And now what I'd like to do is, let me see. Well, what time is it? Is it getting close to break or not yet? You know what I'd like to do is now, So the theorem is this. The theorem is,
okay, should I
what
do
is the
something
theorem?
else?
The theorem is
I'm
this
coming.
right here.
Just give me
So
a
we have
fucking
the theorem.
second.
The sine theta of theta plus 1.
I'm doing something
is
very
1.
important right
So
now.
what we
Hold on
have
1
is,
second.
now we have the theorem. These are all the theorems. So what is this? Theorem, yes. Theorem is this, right? Now it's proven. Make sure you study this proof. And then if you come to the bottom here, we also have this guy here too. This guy's also 1. And this guy's also 1. And this guy's also 1. And so you are free to use any of these formulas. Okay? So now let me prove, let's say this one. Would you know how to prove this one? So let's look at the proof of that one. So what is the example here? Let me prove that. what is the limit of this? What is the limit of? Oops. What is the limit of theta over sine theta? No, tangent theta. Theta is approaching 0. What is this?
Good boy.
For x.
Good boy.
I can use x or
You
theta.
got it. You did good because he saw.
What is this? Why does the limit could be written x or theta? Doesn't matter. Same thing. What is the limit of this guy right here? So it's 1. But how do you know it's 1? How do you know it is 1? We have to show this. So show. Okay? So show that this, okay, how about this? Show this guy. That's what you want to show. Show this guy. How do you show? How do you prove this limit amount here? By assuming this guy. So this is the one we will assume. That is, this is what I will prove here. And then this is the, and then we want to show this. How do you show this? Show this. Okay, so this, at the end, it will eventually become 1. But how does it become 1? That's what you will know. Well, if you apply the, if you substitute theta equals 0, once again, we get the 0 over 0 form. So we cannot plug it in, obviously. So what is this? Now we have to look, now we have to rewrite this, the limit of what? The limit of theta is equal to 0. So now, what are you allowed to use? You are allowed to use this guy right here. Sine theta over theta is 1. Theta approaching 0 is 1. This is what you're allowed to use. You can also allow to use this one too. So now here is going to be what? Is now going to be sine theta over theta and then what is this? This, how about if I just write maybe 1 over cosine, or I can just write actually cosine theta here. I can do this. So the theta over sine theta can actually be written as cosine theta over sine theta over theta. I don't know, does this make sense? The theta over sine theta can be written as cosine theta over sine theta over theta. Algebraically, we can write it this way. So what I did was this tangent theta is sine theta over cosine theta. That's the
Almost
definition.
done.
The sine theta over cosine theta. But the cosine theta will roll on top. And in this theta, I brought it down. Why did I write it down? Why? Because if you write it this way, then now we can apply the limit separately. What is the limit of this cosine theta as the theta is approaching 0? That will be cosine 0 is 1. This guy's 1. Now, what is the limit of the sine theta over theta as theta approaching 0? Now, in this case, we are going to apply a special property or special formula. This sine theta over theta and theta approaching 0, this is actually going to 1. So we end up getting 1. Anyone has a question here?
Right.
Anybody has a question? Now let's go to the next one. I'm going to save this. And now let's do this. How about this? Now let's get to this example. This example right here. Okay, this theorem right here. So now, here's the proof. Let me show you the proof. So the proof, I'm going to write this. The limit of 1 minus cosine theta over theta. And theta is approaching 0. So now let's look at this limit. First, let's look at this limit problem here. So for any kind of limit problem, what is the first thing you have to do? For any kind of limit problem, what's the first thing we have to do? What is the first thing we do on any kind of limit problem? you hear me? Can you all hear me? Are you there?
Yes. Yes.
Okay. So for any kind of limit form, what's the very first thing we're going to do? What's the first thing we do? Now note that this 1 minus cosine theta, this is actually a continuous function on theta. And a theta is, of course, a continuous function of theta. Practically all the functions you have seen so far and you have studied, all the functions you have studied so far, most of them are continuous functions. So polynomials, polynomials including linear, quadratic, the rational functions, and the radical functions, log functions, even exponential, trig, all of them are all continuous. And then the greatest integer function is one of the functions which we get over, which is not continuous, but practically all the functions you know so far, they're continuous. When you look at the graph, they're continuous, except the point where the function is not defined. So they're continuous. In this case, what do you do? Theta is supposed to 0, we plug it in. So when you substitute theta equals 0, so what do you get? Then you get cosine 0 here. What is cosine 0? 1. 1 minus 1 is 0. So we do the 0 over, and then what? 0, 4. So this limit is once again 0 over 0. So once again it's a 0 over 0. Now here, let me tell you the practical rule. For any limit involving any trig functions, what do you need? Need